well, so I'm here to do the honors this evening to welcome our guest lecturer, and it's a great honor and a privilege to welcome Gordon Bell and Sheridan Forbes, who's joining us here this evening as well. You know, I've known Gordon for a long time. I've known of him for a lot longer than I've known him. He was one of my heroes when I was here, even as a student. Gordon, as many of you know, was one of the very early employees at Digital Equipment Corporation, where he is credited, I think very correctly, with kind of inventing the concept of the Minicomputer, which led to so many other developments and really breaking kind of the mold of traditional computing in the world up until that point in many ways. And I think that's a tradition that Gordon's kept doing throughout his career. He was the first director of SCIES at the National Science Foundation, which was the institution that invested in what ultimately became many of the developments that we use nowadays in the internet. There are many laws named after Gordon. One of the ones that I like the best is his definition of the maximum performance of a multi-computer, and Gordon defined that as absolutely positively the speed the computer will never exceed. So, which I think is absolutely appropriate for that technology. He's now a fellow at Microsoft Research, actively involved in research over there in San Francisco. A gentleman who has made contributions in so many areas it would take all night to go through them. He'll tell us a little bit about some of them. I think the one thing I want to summarize before I turn it over to Gordon is that as an entrepreneur, we can learn a lot from Gordon. There are many, many skills that he's demonstrated. One of the most important ones that I think he has is his absolute persistence. When he has an idea and he believes in it, he never gives up. And of all the great entrepreneurs I've ever met, that's the characteristic that makes a difference. So with that, my pleasure to introduce Gordon Bell. Thanks very much.
Hey, thank you. Actually, I want to start with a little bit of preamble, given that this is a history series. And at one point, I was going to write an article about the history of something, and I was talking to Don Knuth, and he said, "Don't do it. They're just too hard to write. They're so finicky. You have to stick with all those details, and then you've got all these people nitpicking everything." So I took his advice, but my brush with history was in the forming of the Computer History Museum, which I hope you'll all visit in Mountain View. So that was a way to deal with that. And in fact, in that brush, that constant brush with history, I always get into this collection of things. Sheridan made a large number of things about history, and they're all good advice. And the one that I kind of like about of history is that first one is a great one of sort of the last person standing writes it, and I've gotten in the brushes I've had with it. One of the things we did, by the way, in the museum was to go out and get all the 20 living people who had built the first computers. Did that about at Digital in 1978. But the interesting thing is the number of people that pop out of the woodwork that talk about what they claim and define. So anyway, beware of history and historians, because they're nothing but stories. The issue is, the only difference between them and fiction is that you have to be constrained by the points. And so history is really deciding which points to pick and which to leave out. And so with that, that's my caveat on the talk and on history. And beware of that as you're listening to all the people talk about history. Anyway, this is really a talk that has about 5 intertwined themes or books. Unfortunately, they're intertwined as opposed to if I had just given them as 5 separate ones, it might make more sense, but I will weave in and out of those. The first one is really this theme of technology, this evolving technology, mostly characterized by Moore's law, but in fact has the corresponding improvements in magnetic materials, in photons, in the development of software, of learning curves, and all of that. So it's really a thing about change. And in that context, I basically say I don't acknowledge that the technology is necessarily disruptive, or I say by definition all technology is disruptive. So I don't really have a lot of sympathy with that there being an innovator's dilemma. It's always changing, and you have to deal with it. And it's really people who are foolish and don't deal with it that I can't condone. So it's really there will be this sort of technology theme and things marked by that, and I hope this will be useful in some of the other classes that you get, because people are getting on and off the curve at different points. Certainly, I'd say Butler and I overlap and have worked in various parts of computer space, but have been dealing with the same technology. The second part I'm going to talk about is really Bell's law, which is a thing that, quote, this is a law that I determined that was in about 1971, and at the same time I also invented Moore's law. Unfortunately, it was 6 years after Moore invented Moore's law, and when I introduced it at one talk, I introduced it that way, that I also had invented it, but it was just a little bit late. But these are this important understanding of how, basically of learning curves, and how we're all on a cycle to evolve computing. So that's sort of the second theme, and there will be a section on Bell's law and how technology is used to determine these computer classes. And then also the part that, until I started thinking about this class, the issue about how they die, and I haven't, and so I need to figure out how death becomes part of the formation process. So we've got the issue of technology, of transistors, the IC, VLSI, and how those have manifested themselves into computers. So that's sort of the second theme. The third theme is about minicomputers as really an example of one of the classes, just like PCs or mainframes or the emerging classes like wireless sensor nets that we're all they're being built right here and created right here in Berkeley before our eyes. The fourth theme is really about DEC and digital as an example of all of this, of all of how things happen. And then, by the way, if we have time, I'll talk a little bit about the culture of DEC, compare a bit with Microsoft, and then how that's all come about in terms of why did it only get to age 41? And I think there are a lot of companies would like to reach age 41. If you, for example, look at where some of the companies are, some of the workstation companies are barely 20 or 25 at this point, and so you have to worry about that. So in a sense, there's a thing that happened with digital. Was in fact DEC was found guilty of violating Moore's law, and it was fatal. The sequence that I'm going to go through here is really one of first DEC starting out, building the first, acquiring transistorized circuits from Lincoln Lab, where the founders came from, and that was sort of a period of 1957 to 1965. Second trial for DEC was really, so I'd say the first trial is really, can you build a company? Second trial was, in fact, can you make a transition to integrated circuits as those came in? And then there was also another little thing with the 1964 when IBM decided that everything would be an 8-bit byte, and that to a certain extent was a trial. There was a trial with VLSI that I participated in, and that was learning to master VLSI and being able to work at a chip level, having really worked at a larger component level. And then as we built VAX and the VAX systems, which Berkeley was a great user of those, and in fact, I think Berkeley Unix was mainly done on the VAX. And the building of clusters came out of some of that effort. And then it entered a period where essentially there were a bunch of different technology changes that occurred. And that was the advent of the killer micro. That is the time when a microprocessor got fast enough to threaten big refrigerator-sized boxes. And now they're sort of pizza-sized boxes. Unix was a part of that. PCs, workstations, CMOS, and Unix are all as standards. And it was at that point that sort of anyone can manufacture a computer. In fact, people did. Michael Dell manufactured them in his dorm room to start. And then,
hey, Gordon, what was your period of time with DEC?
I was at DEC from 1960 as the second computer engineer, and I took a sabbatical in 1966 to 1972. Was on the faculty at Carnegie Mellon, and then I came back from leave of DEC to take a leave from Carnegie. I think I'm still on leave at Carnegie Mellon in 1972, and then I left in 1983. I like to say I sat out the sort of what I call the third generation, that is designing with integrated circuits. Really came back to be able to get DEC into the integrated circuits business. And then DEC in the end failed to exploit a number of things. So kind of that's kind of a 6-step sort of what happened to, or 5 steps, and what happened to DEC in the short form. So I'm starting out by telling you what the punchline is. This are a bunch of references that you have, which I'm not going to go over. So the talk really is got about these 6 parts. The 2 parts up until the main formation of the VAX. And then I want to give this theory of Bell's law of how computer classes form, and then we'll talk about these these more recent stages, and then if we have time, we'll talk about the DEC organization and culture, and a little bit of comparison with Microsoft. Let's see. In a way, DEC came out of I'd say is classic how at least I like to think of the way high-tech companies form, or technology companies form, and that is they work at a university, at a lab. They're doing at the advanced kind of work, and something is there's an opportunity that presents itself in that. In this case, Ken Olsen, Harlan Anderson, and Stan Olsen, Ken's brother, left MIT's Lincoln Lab, they had the understanding to build these transistorized logic circuits. They then went over and they collected $70,000 from a guy by the name of General Dorio, which is considered kind of the one of the founding fathers of venture capital, certainly the founding father in the Boston area, and then started the company. The business plan was to design, manufacture, and sell these circuits. These are AND gates, OR gates, flip-flops, the like, and eventually use that earnings, use the circuits as they built them, and then build a computer. And of course, at the time, it would have been fatal to say, what are we going to do? We're going to form a computer company. Bad idea. And the museum has a lot of the DEC artifacts in there, and then it also has a movie celebrating the PDP-1 and some of the software that was developed there. So here's some financial size and dates, namely things that I found interesting were there was the 70,000 was interesting. The these were 5 megahertz modules. So we're at 5 gigahertz today. So that's a factor of 1,000 change. So things have changed quite a bit. They were profitable their first year, and General Dorio said, "Oh, this is a bad omen. No one's ever been profitable the first year." And so, what did these guys know? They were just engineers, and they said, and the idea was to make money and to be profitable. And so they said, "Well, we designed the system and to stay profitable." The irony was that they almost from the day they opened the door, their inventory went down. I think they opened the door and they bought about $30,000 worth of transistors. These were surface barrier transistors, and then within 6 months, somebody had offered them for about 1/10 the price. So here their inventory, their balance sheet would have looked terrible if they were measured strictly on that basis. The first thing they did was to start manufacturing the modules. They then manufactured some special systems for testing memories. The first computer was the PDP-1, and that first version prototype was sold to Bolt, Beranek and Newman, the company I think we all still recognize today in the research business and the product networking business. I should say what PDP stands for, and it's Programmed Data Processor, because this was at a time when you were maybe selling to the government, and there was a sort of czar, as governments kind of come and go, they're a czar of something, and computers were really scrutinized, but programmed data processors, that's no big deal. And so it was named to avoid.
Gordon, here's our story up here, okay? You remember Ted Kale at the University of Washington?
Yes, I remember.
So Kale at one point had a National Institutes of Health grant to produce a bunch of lab machines. Essentially, this is custom machines for NIH biological lab guys. And the University of Washington had an embargo for some reason on purchasing tape drives. And so Kale wrote a PO for 15 magnetic media manipulators, and it went through.
Right. Sounds right. So it's all about naming. In 1965, the PDP-5, that is really the prototype for the first Mini. And at that same year, we had both the smallest machine that we could think of building, the Minicomputer, and the largest computer we were thinking of doing. Absolutely insane. It's amazing that the company survived all of this. This is a $15 million company coming out with 2 major computers and particularly the PDP-6, which that I architected and was the project engineer of, and was part of the whole starting the whole time sharing. Butler and I argue about whether when the disks got on and whether it swapped or not, whether he was before us or not. But this was a commercial computer, not a lab one of. The PDP-11 came out in '71, and that to solve the address space problem. And then in '78, to solve the address space problem again, we came out with VAX, and then that was the beginning of what I would call kind of a straight up growth. Although DEC, from the time that I came back in, I'd say almost from the beginning, DEC grew at 41% per year, and because I always just used semi-log paper to plot everything, so 41% was pretty nice, because so you double every 2 years.
Remind people of what VAX stands for.
What?
Remind people of what VAX stands for.
Okay, VAX was a name that I had coined to keep us honest as we were doing the design, which is a virtual address extension to the 11. So as opposed to going off to something that would be incompatible and look in a different way, why I wanted to call it the VAX, just to constrain our thinking. So it was a technique to constrain our thinking. In '88, DEC was the #2 computer company, Fortune 38, high market cap, and then by '92, Ken Olsen was removed as the CEO. Alpha came out, the 64-bit computer, and then by 2002, HP had acquired it. So let me go back a bit, and these are the first modules. Note that these little guys right here were transistors. Each of those are a transistor, and this was you put these things together, and then you wired them with patch panels in a patch panel fashion. So they were called logic labs. This was the actual module that when you were going to build something, why it's built the same way we still build things today, which is the modules are a lot bigger today, but in fact these were plugged into a backplane, and then you wired the backplane and so on. This particular module has 6 transistors. So whatever you can make with 6 transistors, you can stack these up and make 2 3-input AND gates, and or gates, or what have you, with just by the way you wire things together. And this was the first system that the company had built prior to '60, and that was a tester for magnetic core memory modules. Here's the PDP-1 prototype that's at the Computer Museum. So you can see these modules back here. There were 25 modules across in a 19-inch rack, and then up to 12 bays of these modules in a 19-inch standard 19-inch rack. I'm here with it at the museum. That's my cell phone that has 2 gigabytes of memory. This baby here had 4 kilowords, and a word was 18 bits. So it's a little over 8 kilobytes. So that was what the change in 1960. It was patterned after the Lincoln Lab TX0. There were about 40 of them sold. I ended up being the project engineer of 20 of them, which was were sold to IT&T for message switching. So this guy came to us and said, gee, we get these messages from Europe. The way we do it now, they come in on a teletype. They come in and are perforated. The messages come in and are perforated on a tape. And then we look at the message, find out, and hang it on a little clothesline, and find out where's that going. And so you move to another reperforator and move that to, and then go and send that out to the destination. Now, I would love to have found out that there's actually two of these computers hooked together in tandem, because it would totally destroy all the history of networking, because that would have been datagram switching. But that wasn't how it worked. These were radial kinds of systems, so the tape came in to the computer and then went out on another line. So it was really just a hub. But if there had only been two of them put together, then this would have been the first packet or datagram switching system. But it wasn't. On the other hand, one of the things that came out of that was I got enamored with serial communication, invented a thing called the UART, which I don't know whether that name still stands for in networking, but that's Universal Asynchronous Receiver Transmitter. And so that's basically a serial line comes in and is synced and converted to parallel, and then brought in, and you read your messages off. That's basically how all the computer-to-computer communication is done today. This is sort of the way we conceptualize the machine in the manual, in the PDP-1 manual. This first, my friends at Livermore looked at this. This is the National Lab at Livermore. Looked at this and said, "Oh my God! Look at all of this stuff. We've got this problem of we want to convert all these tapes to other tape formats. We've got cards. We've got displays that we want to that we've got to read." By the way, I think in all the slides you have all this, but it had a scope and a high precision scope. It had different kinds of tape units. It had card readers, punches, printers, you name it. And Livermore saw this thing and says, "Oh heaven, just what we needed. We want to buy one." And they did. They bought one of everything that we had. The only problem is we hadn't built any of it. None of us had been designed. It was all, gee, this would be nice to have, but then these guys come and buy it, and so we were stuck with having to design all of these things, including a Remington Rand tape controller, Remington Rand tape, and IBM tapes, and I remember fondly remember the card reader, which was the card reader we were offering had some phenomenal capacity, and 1,000 cards a minute or so. And I don't even remember the company who built it, but I remember the guy who was debugging it. And you'd hear this screeching noise, and suddenly all of these cards were all folded up in a little bit, the accordion thing. So it was like an origami device. But anyway, it was. We survived again. Another thing we survived, thanks to IT&T buying production units. This is the PDP-5, which is really the prototype, I think, or archetype for what became the minicomputer and the minicomputer industry, of which there were about 100 companies formed. So the PDP-5 came out of the need to have a controller for a reactor. We had just designed another computer, PDP-4. We had gone we went up to visit the reactor site, which was in Ottawa, in Chalk River, Canada, which is a couple hundred miles north of Ottawa, and find out what they wanted done. And it was I and Ed DeCastro, who was the later formed Data General, and I don't know, a couple of other guys. But I remember coming back from that, about 30 below zero. We drove back that evening to Ottawa, and I said, gee, we don't want to make a specialized thing to control just that reactor. Let's make a computer, because Ed was going to design a special system to make sure the reactor didn't blow up when the computer failed. So let's make it. The way to solve that problem is have another computer that controls it, that's smaller, that may or may not blow up when the. So that we'll have that computer not fail, and the actual control computer will be separated from that. So basically, we came back from that, looked at it. We started out trying to think of, let's build the smallest computer we can, and hence the idea of mini, and not the way I've always classified mini as minimal. That is, take everything out you can and build that machine. So it was, and by definition, it was a really reduced instruction set. I mean, I would defy Dave Patterson to reduce it any more than this. This is all the instructions there. There are 6 memory addressable instructions of 128 words each, and then there was an I/O instruction that that you control things with, and then another instruction called the operated instruction that you could go out and twiddle various bits with that. So anyway, the first machine looked like that. It was a single bay, and I think it was only 4. It had about 100 modules in it. Anyway, that was around 1965, or that same time frame. Relatively in the same time frame, in March 1964, I had been building the largest computer we could think of, and this was the PDP-3, which was a time-sharing computer. So this was at a time when MIT had just built CTSS, a compatible time-sharing system that was running on the 7090. So we said, oh yeah, well we can build one of those, and went off and worked on this and introduced. This was a Business Week article. Recall that in I think it's 47, May 6th or May 7th, 1964 was the announcement of the 360. So this is just preceding the first, the 360 announcement. And then this machine was basically to run multiple teletypes at once. That first machine actually ran. We offered that as a minimum of 16 kilowords, or roughly 64 kilobytes, and it had to do time sharing. So we had 3 users in there. One could be doing editing, one could be compiling or running a Fortran, and one could be doing something else. So, boy, this was really a cramped, really a challenge to get things done in that space.
Was that you?
That's me, yeah. That's me as a youth, and this was Dick Best, who was the beautiful he was the chief engineer. He was a circuits guy, could design any circuit you wanted. But anyway, Dick and I were there before the machine, and about 20 of these were sold, and this was the forerunner to the PDP-10 and the like. I think the other little story about that is just this weekend I got an email from a professor at what used to be Brooklyn Poly, he was writing an article about the change in software engineering. He said, gee, there was a rumor that somebody had written a compiler at DEC and it had one comment, and it was RIP JSB. And it was sort of rest in peace Johann Sebastian Bach. And I know, and he said, is it true? And I said, unfortunately, it's true. The only thing that's not true is it was the PDP-6, not the PDP-4. And he had one comment in this humongous compiler that was the first syntax-directed compiler. And all it had was it was a compiler that had tables of pattern matching, and you had no idea what was going on there in terms of that. I think it took us about 6 months to untangle it. It ended up to being a nice piece of work, but we certainly had no idea what it was doing at the time. And that was the days when programmers were really individuals, and you didn't want to be around. You didn't want to be around the residue after this. These are a bunch of the slides from I took the other day at the museum. This is a PDP-1 as it's ended up. Space War was the first program, I think, that was most interesting program that was run on the PDP-1. That's been used many times to settle a lot of lawsuits on who was the first computer game. So I mean, this machine runs. My grandchildren recently played Space War on it. It has a 5-part compiler, music compiler on it, actually written by the guy who wrote the compiler for the PDP-6, and I've still never disclosed his name. But anyway, but it's truly kind of an inspiration to see this thing run. This was the group at the museum had been working for about a year to get the machine to work again and to make it in a runnable condition. It's in absolutely beautiful shape. The hard part being running the display. That's a 1,000-point, 1,000 by 1,000 display, point plotting display. This is a classic PDP-8. That was the manufactured version of the PDP-5. Came out after in 1966. And the interesting thing about how these things play together was the reason we were able to manufacture it was in making the PDP-6. The biggest problem we had was, geez, we had all these wires. Women had to wire from point to point, so they were wiring twisted pair, lots of wires. I mean, there were 25 times 25 times about 25, I guess, different points that had to be all connected. And I said, that's not going to, we just can't manufacture these. Let's get a wiring machine, a wire wrap machine. It turns out that IBM had pioneered the design of a wire wrap machine done by Gardner Denver. Univac had used it, and so I went off and sort of said, give me a wire wrap machine. And so we ended up getting a wire wrap machine. And what that did applied to this size machine, that is to the small size machine, was it made the thing manufacturable. So we could then turn out these machines like cookies, basically. And that was allowed us to take what had been about a $30,000 machine and now offer that to about $18,000, including a teletype. So what it did was really more than that, make it really manufacturable, and that I'd say was probably the key thing that allowed DEC to get going in Minicomputers. So this was 1965, just prior to the introduction of the integrated circuit. I'd encourage you to use this is the technique that I use to always look at what's going on in how products, product strategy, products, how do you deal with them? That is things that have derivatives from one another, whether it's a compiler or a computer or a chipset for the. And so this poster, which is, by the way, is on my website. We've got here's this machine here starting in 60. It was at the PDP-1 was introduced sort of at the last part of 1960, and then PDP-4 came out, and then this was now a family of 18-bit computers. So I think we were just talking about somebody had just used a PDP-7. Well, PDP-7 is sort of up here. Unix was built on Ken Thompson put Unix on the first PDP-7.
Gordon, question?
Yeah.
UW. It's when I see some of the word links here, 12 bits, 18 bits, I'm always a little surprised because since you're using binary, it almost seems natural to use powers of 2s for word links. What was the logic behind that?
Okay, that was in the first days. There was a 6-bit byte, and people were building basically 6-bit using a 6-bit byte. Virtually all the machines until the 360 was introduced were sort of modulo 6 bits. Control data had a 48-bit word, for example, in their high end. They also had a 12-bit machine, and so in the case of the PDP-8, it was more of, well, I wanted a 9-bit computer just because of the narrowness of what we had to do with it, but we ended up, 3 more bits, and that gave us a lot more capability. For example, in terms of riskiness of the PDP-5, PDP-8, given that first task it had to do was take in a lot of analog inputs, we had a digital analog converter on the accumulator. So you actually programmed the D to A. We subsequently put a similar kind of device to convert it into a UART. So a lot of these were PDP-8s were used as message switching computers, and the only thing the line had was just a single bit to look at the line, and you programmed everything else on it. So that's kind of the 18-bit, the 12-bit, and the PDP-6. So, and notice that they were all coming out about the same time, and the amazing thing was DEC survived all of that, and in large part speaks to the entrepreneurism and to the dedication and the way the company was organized to go off and take each of these things and operate independently. So that really helped. We had a product line by word length basically, and then you'd go off and do some verticals within that. A lot of, in the case of the 18-bit machines, those were predominantly used for a lot of scientific calculation or real-time science, bubble chamber readings, for example, scalars doing pulse height analysis, distributions, things like that. And then the big change really was switching to 16 bits, and that was occurred in 1970. So anyway, this is just it on its size. Okay, so That's really getting DEC started, and now I want to talk about going to what was happening in the industry at that time. So 1965, the integrated circuit came out, or the first integrated circuit, discrete or MSI, medium-scale integrated circuits, small-scale integrated circuits, that is, integrated circuits that had an adder or a few gates on it. And that was, at that point, then, you're lowering the barrier to entry. Namely, anybody could go build, you have all this pent-up creativity, or I'd say it wasn't creativity because they were all alike. 100 companies formed to build minicomputers during the 1965 to 1980, 1965 to 75, 80 time frame, because you could. And everybody had their own idea of, well, I like an instruction set that looked like that, because it was great creativity to design an instruction set, I'd say pseudo creativity. They're not very hard, but they're a lot of fun, and that was allowed a lot of people to go off and create a lot of machines. This is in the book on digital. There's a lot of there's a lot of diagrams, and I'd say this one about semiconductor generations, I think, is an important one. So if you look at the way these are the transistor, I'd say transistor and more kinds of inventions. In 47 was the transistor. The integrated circuit was 58, 4004, 71. And then the first transistorized computers then came out were in 1959, 1960. So the DEC computer came out in that same time frame. But notice it's almost 13 years after the transistor was invented. There were earlier, the TX0 at MIT was earlier. There were a lot of earlier computers, but the first use of transistors in companies was in the 1960 era. And then 1979 was we got together and came up with the Ethernet and LAN. That was a deal that was done with DEC, Intel, and Xerox. So those are sort of low-level technologies. Then you've got these kinds of, I'd say, important dates. The first IC computers integrated circuit computers were 66. There's this mini era which lasted, one could argue maybe it has lasted 20 years. Maybe it still exists. That is, there are still machines that are in that same price range. They're sold by HP. They're sold by Sun. They're refrigerators. They're refrigerator size, but those have been, in a sense, replaced by the notion of clustered machines. 1972 was 1971 was the first micro, but then microcomputers, that is the first use of microprocessors as a computer, was really in 75. And then in 81 and 84, we saw the IBM PC and the Mac, or vice versa. And then that was the beginning of Unix. VAX then played an important part because it was introduced here, and Unix was developed in really here at that time, and was a main driver of the, I'd say, the replacement of the Mini per se. 92 is the World Wide Web, and so on. So the DEC, these red lines are sort of the DEC what DEC was doing at those. I've got some more slides on those. This is a couple of definitions that I had from papers in 1970 and 71 at the introduction of it. This was 1970 when we introduced the PDP-11, and that was when we I think the first use of the Mini, and this was in a footnote, and that was defined as here's how much memory it had, here's what its price was, and this is how many bits it had, and so on. And then in the paper in 71, I basically just defined it in this way. That is, it's really a minimal computer. You take the current technology and then you combine it in the smallest package that you can, trading off everything with software. So I suspected this also fits the risk definition. And then the characteristics were really, it was the minimal computer you can be built at the state of the art, and it's minimal in terms of fixed cost. This you're going to have to get these slides off the net to look at this one. I'm sorry about this, but this was a paper I wrote in 1984. So the mini computer industry per se, I think I tried to sum it up. So here was 20 years of how it all came together, and I'll just sort of read some of these. There were about 50 started up, and 2 grew and continued to have autonomy, and those were Data General and Prime. A few found niches, but then 40 went out of business. Of 10 started up and merged with larger companies, so a couple of those were successful mergers at that point in time. Some of the existing companies that still were existing was DEC and IBM, because I said DEC had made a transition in what it had done. And then in this final category, 25 non-computer companies had built computers, and that included HP. So of this, this is all winnowed down. These 100 winnowed down very rapidly to about 3 or 4, and then those are ones that ended up and survived into the to the 90s.
Question?
Yeah.
What kind of computer replaced the mini computer in 1990? What happened at that time?
What happened was the microprocessor per se took what had been discrete. People had been working at a certain price land. I'll talk about that in the section on the classes. And what happened was the microcomputer came in and was able to, with just in the chip, wipe those out. And so basically you had to use a different structure to get to that same price level. And that's when I came back from Carnegie. The issue was I saw that was going to happen, and so DEC had to get into the VLSI business. So because it's either that or it buys VLSI. DEC could have been easily viable too as an assembler of LSI chips and tried to pack as many as it could. But in fact, the thing is that the overhead structure of a company determines to a large extent what it can deal with. And I've got numbers about why that happens or how that happens.
Follow on to that from the University of Washington.
Yeah.
So when you look at the LSI 11 forward, DEC was essentially building microprocessors, but you couldn't go out and buy a J11. You could buy a processor board. Would things have turned out differently, do you think, if you could have gone out and bought a J11, if DEC had decided to distribute it for a processor?
This was a constant fight and it was sort of 1-8 that I lost. Namely, DEC regarded its corporate jewels as being its architecture. And I regarded that as, yeah, that's nice. That's what we use for trading. And we had many, in fact, the first thing that I did when I came back in 1972 was I went to Silicon Valley because I had all this stuff. Well, there's SOS, there's NMOS, there's PMOS. And in a sense, almost everything I learned about semiconductors was from that trip. I was sitting there with Bob Noyce and Gordon Moore and not Andy Grove, but I think the two of them. And I was trying to give them the PDP-8. You know, please make the PDP-8 for us. Make this as a chipset, and they were already on a course at that point to get to do the 8008. But anyway, I saw that threat coming in, and when we had the J11, the T11 J11, I've got. We had the one chip 11. The theme came back even with VAX. It came in with, we had that same argument with National Semiconductor. I tried to get a deal with them, but in a funny way, National Semi at the time, they had a nice NS 3202, 32-bit machine, near copy of a VAX. It was, you know, but just a little bit different. And so what I wanted to do is get them to make an exact VAX. And then this, of course, within DEC was, oh, you can't ever have we can't have a competitor. People can go out and make computers that will compete with us using our architecture. And I said, well, we do have this stuff called software. Let's utilize that as our as what we sell. But it was a case of I think that was one of the. I don't even put that down as a serious in my flaws that happened. I'd forgotten all those very painful arguments about about standards and proprietary and all of the stuff, all the good stuff you learn in business school, which is absolutely wrong. That is keeping it to yourself. In fact, you know, I think if people had understood what was going on with Ethernet, we probably couldn't have done the deal. It was just, I'll tell you a little bit about the Ethernet story later. But in fact, making that thing a standard was very critical, but yet counter to a lot of the culture at the time where we wanted to do it ourselves.
Another question from Washington.
Yeah.
But didn't sort of the counter argument could be made from the IBM's experience with the IBM PC? I mean, they made that public, and I don't believe they're manufacturing those anymore.
That's right.
So.
But I'll go back to that. I think it might have happened. I don't know. That's one you can rewrite any way you want to. There's many stories there. But because the nice thing is you can't rewrite the future based on the way it could have been. But had IBM gone proprietary, the damn industry wouldn't have formed. Or it would have formed a different way. It might have formed a different way. But it's certainly the rapid proliferation because of a standard, and I'll attribute that to my current employer, that having the standard there is what drove it. In fact, why Microsoft, at least a couple of times I've heard, was never worried about Unix was the fact that there wasn't a standard. Now we're a lot more worried about it because, in fact, there's more of a standard. But until it proliferates and fragments and goes to many different ways, then you can't build the software on that. The whole issue of compatibility to me is a very Very important thing. And I must confess, I'm a standards nut. I like standards so that you can make progress at the next level. But certainly DEC was one at that era, and in fact most companies were keep it that way. In fact, if you look at the IBM 360, which went away, which standardized, basically they just moved the where they get their money from the hardware to the software. So I mean, it's certainly Gene Amdahl likes to plot his graph of what happened to the price of MIPS when the Amdahl, I don't know, 370 or 470 was introduced. Dramatic price shift. This is the PDP-11 11 tree. There's kind of a little interesting story here, and this was as it was being introduced. DEC was behind I was at Carnegie at the time. It turned out that the guys chartered with developing the next follow-on, which is actually to be a 16-bit machine. One of them was Ed DeCastro, and Ed and the crew had developed it, and they got into kind of I had sort of blessed the machine. They came to Carnegie, and I looked at the machine. I said, "Great machine, let's go build it." And it turned out that what happened was they got back, and they got into sort of the political fights that can often happen in a technical company, and left and formed Data General. So here DEC is, my God, what are we going to do? You know, we need a 16-bit machine. We got these 12-bit machines. We got these 18-bit machines. The world wants 16-bit machines. So, there was a crew got assembled to design one, and one of the people that had been a student of mine at Carnegie was on the design team. And although the design was fairly far along, and we had a couple of ideas. Unibus, which was an idea that I had come up with while writing computer structure. So why you write text sometimes is to describe stuff. And so the Unibus was a major, that connection, that bus structure, of which I'm very fond, was one of the earmarks of it. But the other thing was they started to put the design together. They had a design. They came to Carnegie. The team came to Carnegie. There were about 3 of them. And Bill Wolf, who's the president of the National Academy, was a professor there, and I were going to vet the design. So we sat there all weekend looking at this thing. We said, "Oh, this is terrible," you know. And so Harold McFarland, who had been my student, sort of pulls out of his pocket this thing. So here's the machine we had talked about building, and so that, I guess it was, they came in on Friday night or Friday. Sunday, I was the head of the VP who had all of this, called me. He said, "How's it going?" I said, "It's great." He said, "You like the machine?" I said, "Well, we've made a few changes." And so I think all we saved was a board or something like that, but the machine was totally re-architected that weekend, and they went back to use the current what is the current PDP-11. And again, the architecture of the PDP-11 is a concept that, in fact, if you look at the original computer structures which came out in 71, the idea, I came up with the idea of generalize the hell out of the register, generalize everything, and so that whole concept of generality that is the Unibus, the Ethernet, and the architecture there was really came out of writing about all of those things.
So
yeah.
How important was the Unibus, Gordon?
What?
How important was the Unibus to the sort of proliferation of the machine?
In Minicomputers, the I/O I/O is where it's all at. If it has to conceptually look like, oh, I can put my cigarette making machine, or I can put my measurement device, or my communications gear, so that they can interface it cleanly and simply. And so it was really well. I think this goes back to the guy Andy Knowles, who was head of the group at that time, and then marketed it. But it was a super selling point for interfacing. In fact, I'd say, I'll say in the case of the PDP-6, that one of the things that was about the 6 was that we had, in the reference manual, we published the I/O spec, the I/O bus, and the memory bus. And guess what? We created the add-on memory business right there before our very eyes.
So that was going to be my question, which is that you guys opened up the Unibus, but you protected like hell the mass bus.
Exactly.
Right.
And what was the argument there?
The argument is we had to have some place to put the profit. And so the disk, because memories because we had to have the Unibus was open, because otherwise people couldn't connect to it. And then the mass bus was we just absolutely do not want anybody connecting to that. And so
you just basically made the markup on the disks.
Yeah. The markup was because otherwise you sort of have this component, and then everybody flocks to build plug compatibles for whatever level that you operate. So I'm not going to talk about VAX next, but I want to go now into this third point, which is basically the theory of these computer classes, and that is how they form. So we've only kind of really talked about the mini forming, and then the transformations that it's gone through, but it's really one of it applies to everything else. So there are a bunch of laws, I think, that govern sort of manufactured devices, manufactured things, and that's something about demand, and then that doubles or whatever as some price declines by some amount. The big one that I learned about when I wrote, at least explored, was the issue of learning curves. Learning curves are an old idea that I think they were, I don't know when they were really first academically described, but it was sort of World War II, I suspect, early in 40s or so. And that the learning curve says that when you're building something, when you're manufacturing something, every time you double the amount that you've actually done, then the price or the effort or cost or whatever will decline by 10 or 15%. And in a way, that's a part of Moore's law, because there's learning, because you're manufacturing a lot of these different items, but there's more to Moore's law than that, because it doesn't account for the discrete jumps. That's a continuous curve as opposed to the discrete curves that you get in Moore's law when you actually go from across different manufacturing. Bill's law was for Unix at one point. I heard Bill Joy describe that. And then, so we've got Nathan's law about software, and Metcalfe's law about the value of the network. And then,
sorry, could you say in a sentence, please, what these laws are?
I'm going to say,
okay.
Go over them. The one that I kind of like was, I heard Bill Joy give me this law when he came to the National Science Foundation one time. He says, gee, we can't really, no one can write he was bemoaning the Unix problem of getting software, and there's no one can afford to write the software for under 100,000 units. This was when Sun had just attained 100,000 units, and it was sort of saying, well, you've got to write software for our version of Unix. And basically, it's why they're really a Unix software industry on Unix, sort of a shrink wrap thing has never developed. But Bill Gates' software is really, you can't afford to do it for under $1 million. It's probably more like 10 million now. And this is certainly not $10 million, but $100 million. And what you have to do is maintain the price. So these are all things that, in fact, that have gone on in the way pricing and volume relate to competition. Certainly, the fact that SQL Server came out at a $6,000 price versus $100,000 has totally changed the database industry. Certainly, when you can afford a spreadsheet, this tells you when you can afford those kinds of things. But that can all, and right now this is a dilemma that you'd see at a Microsoft, which is, gee, if I put that on a central server, then I can deliver that to 50, 100 million people very rapidly. And so that costs zero, essentially, and all I need to maintain at that level is maybe 10 cents a use or $1 a version or something to get your price back. So this all follows this sort of virtuous economic cycle of some innovation, providing a utility, giving you volume, and competition setting in, which drive innovation. And that's all around, certainly standards enable that cycle to occur. The one I think we all know most about is Moore's Law, which is essentially the doubling of the transistor density doubling or per die doubling every 18 months. And until recently, there's the kind of dilemma of, well, what do you do with that except for caches? But we're into people had for a long time said, well, that's the speed also doubles. Well, the speed has never doubled. At most, it was the square root of that, because that was has to do with line width, and it was all the architectural improvements that allowed speed to improve. But in fact, now people are back on, quote, Moore's Law simply by the way they do the arithmetic, namely by having multiple processors per chip, which Moore's automatically falls out of Moore's Law, or more microprocessors per chip. Intel's talking, 64, 80, some large number of micros per chip, and that's okay as long as somebody can figure out a programming model. But for the last 2 decades, we've been struggling with how the hell do you program these machines. In fact, when I was at NSF, the one piece I had was we want to work on parallelism. Well, it never got worked on. I mean, this was 1986, 88, 20 years later, and I put some very dire numbers on there, like, well, I'll be happy if we get to 1,000 in 10 or 15 years. Well, we are barely at 1,000 for kind of the applications that we have with multiple with clusters of interconnected computers, because we haven't really, we've worked the programming problem, but we've settled on the lowest possible common denominator of MPI to do that. And so I think that's the that's the place where we have a huge amount of challenge and still opportunity today by being able to exploit those. The other thing that has to happen is that all the components have to evolve at the same rate. So storage has to evolve, or has evolved, and it's been at literally at 100% a year for the last decade. So if you look back a decade, you were buying 100 megabyte drives a decade ago. Now those are 100 gigabyte drives in things like this, and then the terabyte drive has just been introduced. So with speed, with transistor density, with memory, all of these things have to go up at the same time. This is going back a bit. This is the price decline of the 12-bit machines, and then the introduction of the first 16-bit machine here, and how these guys were really tracking more of a learning curve price decline as opposed to something that's a new class. This is a graph that from Dave Culler, but he credits me with at least the laws, and that is that these are the I think the best representation of what is the introduction of computer classes. So first computers were room-based. Here's a picture of a whirlwind at MIT in 1953. It was a building, and then mainframes in '64, and it was sort of a room. We reduced that so that with mini-computers to sort of a couple of washing machine size. Workstations came in. These are all coming in at roughly 10x difference in price. And then certainly the PDA coming in, and then he was using that to illustrate the mode that's coming in at whatever, modes will ultimately settle on maybe $1 or less per, but once the applications are formed to take on. But in fact, so what's happening here are new computer classes are forming. He says log of people per computer, but it's also log of the price of the machine. Something has happened in the last few, I'd say since 90, for the last decade, what's happened is really scalable computers have come in and are sort of wiping everything out. There's sort of, it's a kind of a winner-take-all with, now let's build them out of the smallest component we can, namely a PC, and let's put those together. It turns out that Jim Gray and I got together in fact, Jim gave a talk here in 1994 on a thing we call SNAP. And we said, because Jim had worked at DEC. He worked after I had left. But Jim and I decided that we shared the same religion. And the religion is that everything is going to be built out of PCs. And that you're simply going to put as many of those together, and that was going to be the machine structure that was going to take everything. And so we defined a thing called SNAP, which is Scalable Networks and Platforms. At the time, we said it was going to be ATM connecting all of those, because ATM would be a long distance, and it looked okay. But but we forgot the phone company was involved with ATM, and anytime the phone company's involved, it's going to get screwed up. But yeah, 5 minutes? Okay. Yeah, I'll just finish this little section. And so anyway, Jim and I got together with our religion, and of course, like any religion, we don't like anybody else's religion. I had just come off of a 30 from 1960 with the PDP-6 to, I'd say, 30 years of being in the multiprocessor religion. I gave it up in 94, 95, saying it's hopeless. It's just too hard making multiprocessors that can scale. So I got it. I wanted my machines to scale, and so we determined that was hopeless, and we went to scale. The only way to scale is to use computers and to scale at that level. And then, lo and behold, if you look at what's today, we're back to where we were. This is the large server. I don't know that we've got any that have got 1 million processors in there yet, but there's certainly some that are out there with 100,000 computers, processors as a single machine. So looks almost exactly like the BARTA building that I showed in that first picture, which it looked like a telephone exchange with all of those racks and racks of flip-flops. So a flip-flop was in that machine. A flip-flop was this big, and you can see one. And a bit slice went with 4 or 5 bits went from floor to ceiling. You can see one of those at the Computer History Museum. But now these machines, we're building buildings around them. And where do you locate them? You locate them near where you get cheap power. So you look for natural gas, whatever. In fact, I've had proposals. Where do we want to have one? Could we put a supercomputer in Perth? Perth, Australia, because there's a lot of natural gas there, and some of the gas friends know about. How about putting our machines in Perth?
Hey, Gordon?
Yeah.
Google's server farm in the Dalles, Oregon is actually on the site of a former aluminum plant.
Right. Sounds right. So the transformers are already in place, and these guys all take about anywhere from 5 to 10 megawatts to power them and the like. So anyway, we're back to the computer is the building. And in fact, so scalable computers, so you say, what's happened? We basically have wiped out mainframes, we've wiped out minicomputers, and this is kind of the way we've decided to build our computers as of today. So anyway, let's take a little break, and then I'll continue on this.
Great.
So anyway, this is sort of what we've settled on as the architecture, and how that had gotten represented, how Jim and I had represented it in '96 was, in fact, we saw what had been these sort of price bands, PCs above $1,000 to $2,000 or $3,000, workstations here which have actually gotten squeezed out. And what do you mean workstations? What are those? Mini computers that were at the multiple thousands going up to 100,000 or so, mainframes up in this band. So I had seen this had been my canonical price band kind of set of structures, and then in the 90s we saw basically this architecture coming in and basically overtaking all of those other architectures. Okay, here's what I'm claiming is my law about computer classes, namely that the technology improvements, particularly Moore's law, but also disks and everything else, allows 2 evolutionary paths for computers. One is at this constant price and increased performance. Namely, you get more, but you pay about the same. And then the other one, which is the interesting one, is this new class forming. Namely, you take whatever you can in performance, you decrease the cost by some factor, hopefully like 10x. That leads to a new structure, a new computer. In about mid-70s, I sort of plotted it like this, which is in fact showing these two evolutionary paths that created these machines. These are taken from the book on either High Tech Ventures, or I think these came from the book by that we wrote on about the DEC computers, and then showing again these different constant price computers staying constant price, and then these are constant performance. So we're seeing new platforms forming as you come down in price. If you look at the numbers, why that has to happen is that it's kind of a conspiracy among marketing engineers and customers. Namely, if you ask your current customer what they want another machine at about that same price because their overhead's all been established and they want to get more productivity out of it. But the thing that you're after is really, if you just simply say, well, I'll give it to you at a tenth the price, that doesn't really do very much for them from a productivity standpoint, because it says, you mean, well, I can buy your new machine at a tenth the price, but I still have the old software, I've still got to maintain everything, and things really haven't changed a great deal. So a couple of things are going on here. This price performance issue is happening, and we're entering new price bands. One of the things that I've tracked it over time, if you look at that, then there's car prices are like that, transportation is like that, from everything from shoes to ICBMs. French restaurants, this is data I took in '95, which was that this is some function of ambience and location times $25 times 1.5 raised to the number of Michelin stars in a restaurant forms a new price class. So if you don't believe me, go to a 3-star restaurant and see how much you pay in that. But these numbers are all changed a bit, but in fact that's the basic idea of the price class. So we form these different price bands, whether it's cars or restaurants or what. Yeah.
Question to you, Doug. So you were talking about the conspiracy sort of inside the industry, and you were talking about, well, if my computer costs 1/10, but it only does the same thing your old one does, there's sort of no reason to migrate. How has that changed now, since the operating costs of computers are often dominating with power and data centers, rather than the fixed cost of just buying a computer?
Well, I think all that will happen is that there's been more standardization of the platform, and so probably if your operating costs can be decreased, well, then you go do that. Things like virtualization, that allows you to have less computers and to do better spreading of load. So those things are all going for operational cost. I think for a given established price, then people will do what they can to get the next increment in power out of that, whether it's more I/O, more disk capacity, or what have you, to take advantage of what they have invested in the legacy software or legacy data, most likely. The other thing about new computer classes, is essentially we have several components to a class. Namely, it's a new platform. That is, to have a new class, I think you have to have a new platform. That is something that really is dramatically different. Not just another version of an operating system. I'm talking about something that's not just subject to the usual learning curve of continual price decline that you get by more volume, which we see in which we see in ordinary PCs, that those have come down in price. But it really has to have these other components. That is, it has to have a new interface to something, humans or part of the physical world. It has to have a new networking or interconnect structure, how it's put together. It has to have new applications, and it has to have, and ultimately the result of all that will be new industries will form from that. That's been true of minis. It's true of workstations. It was true of micros. PCs have been that way, and now PDAs formed in that regard. PDAs and then merging with cell phones, and then I'm now predicating that this is the new platform. In fact, we've got a bet out. No one will take me up on it. This is the Microsoft terminology, small form factor devices, and I had called them cell phone sized devices, are going to overtake the PC as the dominant platform, certainly for the world. And the question is, how far can those things go in terms of doing what the PC does? The other class that I think is forming is this sensor modes class that, in fact, that allows the ubiquity of wirelessness. And that's one that's really it's now in its formative stages. We've got the dust networks that came from Berkeley. David Culler's got a company that's predicated on sensors. Crossbow has been in existence for over a decade now, but really that had come from a sensor point of view. The other guys have come from a wireless point of view. And then what's going to happen there, I do not know, because it has to be an issue of standards. And I think the standards are just now beginning. There's a thing called Zigbee that the company called Ember on the East Coast has been driving. Other companies, there are X15.4 radios, part of that. But then there's this other thing that's really intriguing. It's called Wi-Fi. That is 802.11. And there's an Australian company that's got an absolutely gorgeous chip. And so you've got to ask, why do I want to invent another network when I'm building this great infrastructure now called Wi-Fi for ubiquitously connecting everything? But the Zigbee guys are saying, oh, it's all going to be wireless into a home. We're going to wire our thing with a Zigbee net. And I say, wait a minute, I've already got 15.4 in my home. I don't want another net. I'll have my bathroom scales connect to the 15.4 that's or to Ethernet that's already there. So anyway, these are all the earmarks of a class. So you know you've got something new when you see new kinds of application, new uses that we're seeing. I mean, and I'd put the iPod and the Zune or Zuni or whatever the Microsoft device is that came out. Anyway, I have to wait until I get mine. I've been a steadfast holdout for not having an iPod, and so I'll wait for our product. Anyway, those are all kinds of things that I think allow you to say you've got a new computer class, and then you take off on that basis. By the way, one of the classes an intermediate class that formed here was our friends with the World Wide Web. So the PC came in the 80s, 85 to 95 or so, but then that really kicked in to a new platform with the introduction of the World Wide Web, where the PC was just the just a component in that.
Gordon?
Yeah.
A question from Washington.
Yeah.
Would you consider the transition from command line interface to graphical user interface sufficient to constitute a new class?
Absolutely. This was back a slide I didn't put in, which was PCs. The WIMP totally changed from what had been a command line terminal interface to really constitute a new class, new set of users, new applications, and so on, just as I consider this to be a new class. And lo and behold, they are separated in the order of about 12 years between the classes. Here are some of the price tier things that have come into being, and so that varies from $1 up to sort of $100 million for the various large centers. Another way of looking at it is this sort of, if you look at this sort of pyramid of machines, that there will be one computer. There is one computer today that is the largest computer. I don't know. It's probably Google has it or somebody has it, which has got 100,000 processors in it. Takes more power, can compute more, has more data than any other machine. You go down this sort of pyramid and you form computers being formed like this with 10,000s of corporate environments where you've got 1,000-node kinds of machines. And then if you go into your home, why our typical home networks are maybe 5 to 10. Then you get into the small form factor devices, and here we've got a few billion of those in existence today, or that are out there that potentially will evolve. When you say the cell phone will ultimately take all, and then this ubiquity land, there will actually be trillions there where everything now gets electrified and takes on that role. If you let me say just kind of what happened is that the industry as it evolved. As you looked at it in 1982, we had a sort of a vertically integrated industry from semiconductors through processors to computers and on to even solutions. Although IBM was the only one that really had solutions there, and then that moved to this kind of an industry, disintegrated industry in the mid 80s. With standards taking on, so that in fact this was a horizontal industry or a disintegrated industry where each layer is now kind of a sub-industry by itself. So anyway, that's what seems to happen in a class. So once a class is established, then you start to let that evolve. These subclasses or subcomponents will come in and take over. So I'm kind of that's the end of the stuff on this computer class formation. I hope I've convinced you that that's what they are, how they form, why they form, what's the economics behind them, and what they're all about. And so you can watch for them, because right now we're looking for the next one. I mean, it's kind of like particle physics, but you only see it a decade or so after they've happened. Now I want to go quickly over the VAX strategy, how that came into existence, how it got DEC up to number 2, and then that'll put us in time for why that was just made DEC go up, and now everything that goes up may have to come down. So here we are. When we first left the PDP-11, we got to VAX, and that was in It was introduced in 1977, and that we said before, it's the virtual address extension to the PDP-11. In some sense, it was a good time and a bad time because it was 4 or 5 years too early to do RISC, because RISC required having a very fast memory for cache memory, larger cache memory. So it really was the last of the CISC computers. It was a computer that, in fact, had every instruction that you could imagine. We had it had a COBOL. There was a COBOL machine in there, so it compiled. You basically compiled COBOL almost 1-to-1 as an instruction.
I know the poly instruction was.
The polynomial evaluation instruction was. I just forgot about that. There was a queue and in-queue instruction in there. Put a thing on a queue. So it was a very the ultimate in instruction sets, and that was at a time when the technology was all set to do that, because it had the VAX 11, the 780 had I think an 80-bit microprogrammed word, and it was about 6 times faster than the outside machine, which was constrained by memory. The VAX came in. We started the project on the 1st of April in '75. I was leading the group. Dave Cutler, who was Dave Cutler's done more, has probably written more software for more machines than anyone I know. Namely, he had done the RSX 11M operating system. He was responsible for VMS, and then he went to Microsoft and did NT, and then recently he got NT running with 64 bits. So basically, almost everything people compute on, I say Dave has had a hand in, certainly more than anyone than I know of. And I think this is from the blue book that we had. So we had a little working group, and this was a 6-person working group, and that's sort of we met in one. We got up in one corner of the DEC mill, and this is what I had written about the PDP-11, and basically it said, gee, in 1969, we really had screwed up because we ran out of address bits really only 6 years after we had introduced the PDP-11. And now, it turns out there's an article in Q Magazine this month that I recommend you all read. This is if you're into architecture. This is John Massey, and it's called The Struggle or something like that, The Long Slow March to 64 Bits. And it's a wonderful article about all of the thing. I think it leads with my quote. This was from a paper that I had written. There's only one mistake that can be made in computer design that is difficult to recover from: not providing enough address bits for memory and memory management. And so the PDP-11 followed that tradition. We extended it several ways. VAX 11 was compatible with that. There was a PDP-11 instruction set built in, and there was a mode, and you could go run there, which, by the way, turned out to be very valuable, because that was how we brought all the software. We had all the software running immediately on PDP-11s, and that came right over Fortran and all the utilities. and so it was a kind of a shame. Well, we screwed that one up, and then about a decade later, why alpha had to be created, and that was introduced in '90. The interesting thing was, did we know what was going to happen? And this is from March 1975, when I was doing the planning for this, and here's a much better version of that, which is essentially, this says these are different system price. I had gotten all of the pricing and evolution of computer prices down to a single variable, the price of the bit, and it was simply how much memory you had, and this was the planning model. So, and the amount of memory a machine had determined what it would be used for. And so, in looking at this is one of these things of, you look at it and you say, well, we've got this computer here that has a megabyte, and gee, that would have been a $10 million computer. But when we were here, we had $1 million machine at this price level. But if you ran that out to 2000, oh my God, that's going to be a $10,000 computer. What are we going to do? And it was one of these things. If you you run these exponentials out and you say, oh my God, what is going to happen? So we knew something big was going to happen, and how it wasn't clear exactly how it was all going to play out. But what we did know, that the price was going to be declining at this very rapid rate. And so machines our old friends, many computers that we knew and loved that were selling for maybe $10,000 in '78. Here's when it was introduced. So machines that were in this price band were suddenly down. In '90, they were going to be selling for a factor of 15 lower. What are you going to do about markup? How is that all going to? What's going to be the effect of these tremendous price declines that we're going to see? So all we could say is, make sure we put enough address bits in there so that we can exploit that to a certain extent. This is the beginning of when, I'd say, the beginning of when the VAX strategy was put in place, and how we viewed it was all that VAX was all going to take off. And this was a strategy that I had come up with while scuba diving for 3 weeks in Tahiti in the summer of '77. I came back from that. I said, we've got to scrap all the things we're doing, and we're just going to go to a single architecture. Sound familiar? All the wood behind one arrow, and we're going to make VAX in different price bands. And the other thing that's different than the idea that came from the 360 put them all different kinds of. They were still all mainframes. They were all used the same way. In this case, it was really the way the architecture was described was in a form of an E. That is, we were going to have a clusters here. So these were all kind of a cluster here. So we weren't going to make mainframes, but we were going to make the biggest computer we could make that was sort of right from a price performance standpoint, and we were going to cluster those together. And that was the idea of the VAX cluster. So that was at the top level. This was how we were going to go after IBM, which was, don't make mainframes, just make big computers and put them together in modules. Then we had our good old friends, the minis here, that were going to be put together here. They're going to be distributed throughout. These are going to be distributed minis, and you put them in closet, you put them in labs or whatever, and then turned out we had a network interconnect that connected all of this stuff, and this was so we needed a way to connect all those together. And that was called the network interconnect. So now I came back and posited this whole thing, and then down here we've got personal computers and personal VAXs. We're going to use PCs until we got VAX and workstations at that level. So it was a 3-tier architecture which allowed you to have mainframe kind of capacity at the high end, minis, distributed minis in the middle, and then PCs fully distributed and workstations at the low end, and that those were all going to be connected, interconnected, so you could move jobs anywhere, do anything, any place you wanted. We had very good networking technology called DECnet at the time. IP hadn't quite come in as the standard, but it turned out not to be a big deal when we had to make that switch. But the issue was compatibility. You could take a job here and run it anywhere in that whole hierarchy. It was like the IBM announcement, 1964 announcement, where they decided to have one architecture throughout their whole product line, with a few outliers. They had other smaller machine set of outliers too, but that was the basic idea. And
I have a question from you, Doug.
Yeah.
I ran one of these big environments back around 1988, and by way of kind of background, we had a big IBM mainframe shop in the same location. And the way that IBM tackled this was with a system called Sysplex, where you can move around batch jobs between processors. It was big and complicated and cumbersome. And if we went over to our DEC side, we had this beautiful DECnet environment that everybody loved. Sometime around that same era, Sun came out with the TCP suite and said, well, here's this personal workstation you could plop on your desk. And we would take them to our DEC machine room and say, well, we can do the same thing with this beautiful microVAX and later on the VAX station. And it always came to mind, how come DEC didn't seize the microVAX and VAX station and compete head-on with Sun and probably could have owned that whole industry?
That whole thing is that's part of the tragic tale of DEC. It really, because our biggest problem there was to get the VAX down in price as quickly as we could, and we did. But that was at a time I'd had a heart attack in '83, by the way, and so I said, gee, maybe this job is too stressful for me, and I don't think I want to give up my life for the company, and whether it was stress or not, but anyway, Ken and I always were probably I was the only one who could really argue or did argue with Ken, and I decided it really had taken a toll on my body, and I really wasn't up to doing much more of that. But Ken I was much more of do what's right and put everything on that and just go for it. And Ken was, well, we got all these different, there's a workstation. Gee, Sun is out there. We need a workstation. And lo and behold, you go into DEC engineering. There was 6,000 engineers at DEC. Oh, you want a workstation? Oh, I happen to have a workstation here for you. It runs MIPS. And so we've got that. Oh, I got a PC workstation. And so everybody had a solution. And DEC in 1988, they had introduced 7 different platforms. So we had gone from a workstation, a single platform. Notice, compute anywhere without any reprogramming or anything in a distributed system across this whole hierarchy to, oh, you want PCs? We got those PCs. You want this version of Unix? We got a version of Unix that does that. DEC was, not that I didn't acknowledge Unix, because in the 6 people that were part of that, we allowed one marketing, I think we had 3 marketing guys. They could come in every 2 weeks and talk to us. And then the other thing is we only had one customer we talked to, and that was Ken Thompson. He said, how does it run on, what do you need to run Unix on it? And so that was fundamentally our marketing input. I mean, if these guys been building computers for a long time, didn't know how to build a computer or what they did, why, customer input's not going to help us. But anyway, the biggest problem there was the fact that Ken had a philosophy of we give people all these choices, not understanding the fact that every damn choice was confusing to the sales guys, it was confusing to the customer, and above all, it was very expensive to maintain. Every platform you put out, has a huge cost to keep the things.
So Gordon, this is Ed. Two points I'd add. One is, I remember at one point early on, DEC had 3 indistinguishable PCs. There was the Rainbow and the this and the that. And
that was absolutely, and that was absolute classic.
And the way somebody explained this to me was nobody likes to kill puppies. That is, you would have competing people with competing platforms, and then somebody really needed to shoot 2 of them, and that didn't happen. There was the one which was the evolution, and that was the PDP-8, and that there was some software. It was used for word processing. I think of it as that was the typewriter. And so, in a sense, to the extent that we ran in a divisional sense, we ran the PDP-8 that way. The PDP-8 was long obsolete at that point, but yet we had a small engineering crew. We could introduce the things very cheaply, and in fact, people continued to buy them as, in this case, as typewriters. I almost don't count that, but the main one, the Pro or whatever, the PDP-11, we had a beautiful bus, did all the things that the IBM should have done, but would we allow anybody to connect to it? Would we publish the bus? Absolutely not. People might add stuff onto it the way they did on the PC, and then yet we had in the case of the PC, having the PC there, we had an advocate. In fact, including myself, gee, this thing may just take off, and it's going to be a standards and a pricing issue if that happens. It's manufacturing and it's standards, and you just got to be there with that at the time. So. If I killed anything, I would have not bothered with the 11 at that point. Yeah. So one other comment is, I remember that DEC made a huge number of concessions to try and get DARPA to choose VMS as its operating systems platform instead of Unix, what became Berkeley Unix, and history would have been very different if that had happened.
Right, and that whole story, in terms of how that was, botched overall. I mean, Sheridan. I'm not going to get in. Sheridan has the story of Ken saying no. We had the opportunity to have been given Unix from AT&T because they said, "Gee, we make telephones. What are we doing with this piece of operating system?" And so apparently, DEC had the option of picking that up and didn't do it. But on the other hand, its feeling about standards at the time, I don't know that it could have dealt with it. The point is, it didn't understand the issue of standards. I'd say the other thing about the VAC strategy here, that really one of the main things that came out of this was the NI, which is called Ethernet, and we made the deal with because I drew this thing on the board. We knew that local area networks were going to be important. There weren't any local area networks other than a few. There's ArcNet. Xerox PARC had a 3 megabit network. And so we desperately needed a network. So we went off, and lo and behold, Bob Metcalf had just escaped from PARC and came to us and said, "Hey, would you like to have would you like to have an Ethernet? And we said, yeah, that looks pretty good, because to me it looked just like a unibus. Well, you have a lot of things, and you hang different nodes on this 2.5 meter, 2.5 kilometer piece of wire. Sure, we want to do that, and during that process, we made the deal with Intel, with DEC, with Xerox, and Intel. The interesting thing on the Intel thing, it was the first use of the picture phone meeting service I had, which is I went to a room in Boston. Phil Kaufman went to a room in San Francisco. We shook hands. Yeah, we're going to do the Ethernet deal with one another, and then on the same kind of thing, Dave Liddell came to DEC, and I remember, and unfortunately in all the documents I can't find the document where, Xerox had come and said, gee, we want to do now it would be a good idea if we get together on Ethernet as a standard. And so they were about to walk out the door, and I said, oh, I hadn't been part of the meeting, and they said, what are you going to, I said, okay, what are we going to do? He said, well, we've got to get back to our management and blah, 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 and do all this stuff. I said, what do you need? He said, we need a letter from DEC saying, let's do the deal. So I said, what do you want it to say? And I sat down at a word processor and typed the thing, and I said, here's the letter, take it to your commander, and let's get the thing going. And so that was the first thing that had kicked it off. We included Intel after that because we wanted somebody to make some chips, and then that was the origin of it. Intel used to come back to us every 3 months or so and say, gee, Olivetti wants to be part of this whole consortium, or so-and-so wants to be part. And I said, no way. We've got 8 guys doing the standard. I don't even go and talk to them. So if you think I'm going to let Olivetti come in and try to say what's going to be, and then I got a call from the chairman of ICL one Saturday night, and he said, hey, I can bring in Europe if you'll just open your kimono a little bit. And I said, come on over. And he brought several technical guys over. We agreed that this was being done in the right way. They added a couple bits here or there or whatever. Got this, and then we got this. Basically, it was the small group of people did the standard. We had a working prototype, and then we put the blue book out and said this is what the standard was. We announced it at the World Trade Center in February of 1982. Liddell, Bob Noyce, and I were on the program and made the announcement. And I remember someone from Business Week asking, well, what about Wang Band? Wang was, they're going to use a cable TV thing for their local area network. And I said, well, I don't know who's got much cable TV in most corporations or universities or organizations. And then I said, well, the problem with Wang Band is think of a cable TV as like a piping system for a city. You got sewage, you got water, and you got gas. And now, in principle, we can put them all in one pipe. Right. But in fact, sorting them out is the tricky part. And so I think that got quoted in Business Week, which is where but it's just a bad idea. And so I think we're finally getting there with it. But anyway, so this was this is what the VAX strategy was sort of in. DEC had a market cap that had been growing nicely. This was the market value. And this is really the VAX strategy kicks in during this period and then reached a peak and then started a decline. Ken was let go of the company in '92, and then that's when Palmer took over, and it took him about 8 years to sell it to Compaq or to be acquired by Compaq, and then then HP acquired Compaq. But anyway, that's kind of at least from that point of view, what happened. What really happened at the sort of in that same era, let's look at this. This is I had just left DEC in '83, and we were going to start a little company. That's a different story. Don't even want to go there. But this is a slide that I put together when I got out there, and I said, this is what startups are looking like at this point in time. Basically, there's this, if your frustration is greater than the reward and your greed is greater than fear, then you begin a company. So you get a PC and a spreadsheet. If you've got a system company, then you beat the VAX plan, and you write the plan. You get money, and then you exit. Then you exit the job, and you start to. So there was a bit of morality in this whole thing. Most people were starting companies right on the job with the other. And then here's the essence of it. You get a Unix license, some developers, some VAX. You get a VAX to do all the development on, some development tools. You build a product and so on. You sell it for 100 times the sales, and then you take that money and become a venture capitalist. So anyway, this was done in '84, '85 when I said, what are you doing? I said, well, this is what the market is all about. It's about standard. It's about Unix. It's about these licenses. You're going to go out and build these computers, and this is kind of. And if you were doing PCs, it was even easier than that because you assembled it in your dorm room. And Michael Dell, I don't think did anything other than plug. At most, probably never did any soldering, I would guess. I think they were all. By then, you could plug everything together. But anyway, that was the era. That was what's happening in the 80s when Unix was going, workstations were going, when Sun was formed, when the PC was taking off, and so on. This is a piece of technology this is a really important piece of technology. This set of curves here is really what was happening with the transition. Namely, here you got TTL. DEC was making computers with TTL at the time. IBM, Hitachi, Fujitsu, NEC, CDC were all making ECL technology. So you had a factor of 3 or 4 difference in performance. You had them on the same slope. Then suddenly you've got this thing called CMOS coming in. Here's the 68K coming in. Well, I'm not worried about that because look that's a factor of 3 or 4 lower price or lower performance. These are performance in VAX units. That's not important. But what was important that this was on a slope that ultimately was going to overtake TTL, and that's what happened. And a lot of people were wiped out in this whole thing. In fact 1980, it was 1980 about this time. We were on good terms with Control Data. They asked me to come and give a talk. I was there from NSF. They said, here, look at our new mainframe. And they opened up this big bay of stuff. I think it may be a dual processor or something like that. All Echo, almost discrete technology. And I said, well, how fast is it? And they said, 3 MIPS or some damn thing like that. And I said, you're toast. You absolutely are toast. do you realize that I can go buy a CMOS chip that will outperform all of these racks and racks of stuff? And they were toast. But it's really kind of pathetic because they were sort of sitting up there in the snow and cold and hadn't really seen what was going on in sunny California and what was going on with CMOS. Almost as pathetic, I'd say not almost, far more pathetic was what Ken did in terms of the same thing was in this machine here. This is the 9000. This was the DEC mainframe. That was going to come in, and sure enough, it was going to take over mainframe. It had mainframe capacity. It had all those capabilities. The only problem was CMOS was just about as good, or was as good when all the smoke cleared. And really what happened there, DEC spent $3 billion building an ECL mainframe at a point when CMOS had fundamentally wiped it out. And the only reason I'll quote this, make this comment, is that in fact in Ed Schein's book, which you have a reference, is that it's not apparently not a hearsay, which is Ken had made some statement about some point in time in here. Basically, he said, "You mean to say that 2-bay mainframe we just introduced is no more powerful than the CMOS microvacs microvac chip that we've just introduced in Workstation?" And they said yes, and they were toast, or Ken was very, very soon toast. So the ECL, making the ECL transition was a big deal. IBM had screwed did the same thing, had gone too long on the thing. CDC was wiped out because of it, and although I think it would have been anyway. Fujitsu went too long. The only guy who I think who did something right there is NEC switched to CMOS very early with their high performance machines, and they had mastered that, and they still make essentially the fastest supercomputers. So anyway, that's that whole set of things. The other thing that was happening here, this was a paper I had written in 1985, and I was predicating the world that all the world is going to be built on that structure. Namely, my good old friend, the Unibus. And now, instead of just one processor, you put multiple processors there, and then you put the memory on that same bus. And then, for the first time, nature is working in the right way. Namely, with the cache memory there, you're able to filter or limit the number of requests that are needed to primary memory. And so this structure formed as, I called it a multi. The name hasn't stick, but in fact the structure has, and that's basically how we build all up to a point. This is kind of how we build all computers today that are bigger than a single processor. So it's a shared memory thing. Recall, my religion was I only build multiprocessors, and that was from 1960 to 95. And I worked on about 30 of them, and I thought this is the only way to build a computer because you got to have a shared memory. But I gave up at that point and said, you can't have a shared memory. It doesn't scale. It's too expensive. Blah blah blah. Let's figure out how to program it, and we're still working on that problem. So anyway, this structure came in. A lot of computers were formed there. Sun made their machines. Ultimately, all the guys who had made microprocessors were out there. These were all going right for the throat of DEC. So DEC hadn't moved into this structure either at that point in time, and that tended to be another thing that happened there. So kind of in summary, then DEC had done right in transistors, they had survived the IC 16-bit transition. They had survived being able to make VLSI. They had failed to embrace the PC. They had failed in this TTL and ECHL transition. They had spent too much money there, and therefore had missed the opportunity and to move into the right structure. And they certainly, when this thing came in Ken's inimitable way, basically, he took that as an opportunity to go off and make a lot of computers. That's when, oh, you mean I can go get a Unix license and make, 2 or 3 different versions of Unix. I can get can sell the MIPS system. And at that point, DEC had 7 separate platforms, and that's a lot to maintain. I recall when Microsoft was able to go from Windows 95 to NT, which to me was a miracle, to get that down to a single body of code, because these things are really hard to maintain. So there was a whole bunch of things that happened in terms of standardization, exploiting the opportunities that DEC screwed up on. But then the other thing was probably as bad as all of that, was they had opportunities here with the web and Alta Vista. They were first there. They had servers, they had clients, and that was a failure to exploit all that. That was the thing, in a sense, that was what got Sun into so much trouble. Because Sun went out, they looked at the DEC stuff and said, wow, this is right. The chief technical officer of Sun today, whose name I forget, basically looked at that, said, that's what we're going to do. They did that and then simply outmarketed DEC.
Papadopoulos?
No, it was before. He was in charge of the networking. John Gage. John.
Wow. I didn't know John did that. We all know John. We just didn't know he.
Yeah, he got the design from DEC had all of those.
He lives in Berkeley down there.
Yeah, but anyway, and so John was able. That was all useful and Sun exploited that beautifully. Now that's the good news. The bad news was they sold a lot of refrigerators. The normal DEC, would have been a DEC, these very large servers things, and people. It was amazing. A startup would say, well, we need $1 million to buy a Sun server. But you don't have any clients, you don't have any traffic. Why? Well, we're going to get traffic. Oh, and they were getting Oracle, they were doing all this, all these other things, but then that didn't, that was one of the things. So I'd say DEC not doing that. And then DEC had a lot of other opportunities, like printers. They were stronger than HP in the early 80s in printers. They had the whole printer market. They had the printing terminal market, for example. They had the first laser printer as a computer peripheral, although Park had certainly built one of the first, Park had built the first laser printer.
Sorry,
CMU
Apple,
had built.
the Apple Laser Writer preceded DEC's laser printers, didn't it?
It might have. They were probably used the same engine.
Yeah, I think that's right. You're right.
I think the main thing that one of the things I had done was with Forrest. When Forrest had established the Whirl, we went to Adobe. I think Adobe was just starting up and said, "Gee, will you make that for us?" And so they basically put PostScript in.
I was there at 85 the day they released it, Apple. And Apple actually, when they were a startup, Apple actually invested in Adobe and did quite well with the shares that they held.
Yeah.
You guys used to do a lot of work on disk drives too. That was a big part of DEC.
Oh, DEC had a huge disk drive, and they had a very high performance tape. And I think the tape is still remnants of the tape business are still there in a different form. So anyway, we're back to, well, that's really, the sequence there is really this quadruple whammy that happened starting in 83 that while DEC was on the VAX ramp, they sort of, the nice thing about the VAX strategy is you didn't have to think. The whole company was behind it. It was so simple, and they didn't think. That was the problem. And then the other thing is this failure to exploit what you have. So there's, in a nutshell, that's kind of it. If you look, if you've got time, I encourage you to go look at the slides, because I've got two, Paul Campus and Pete DeLisi were at DEC at various times, and they've got different descriptions of what they think happened. By the way, and they pretty much agree with with what I've said. And they've got, in a way, they've got different representation. And I think you'll find, particularly Paul's stuff is very good in terms of providing a background on the whole industry. So as you're looking at these other talks, you can use those slides as a kind of background slide. The 8600, one of the problems there was that it was late. This was our first attempt to make ECHL using gate arrays. This was not done in the VLSI group, but it was done in the CPU group. We had gotten the VLSI group going, and they were going like gangbusters, but the CPU groups had not, the big CPU groups had not switched over to thinking CMOS at that time. So there was a kind of a cultural shift there. But basically, it was introduced too late. Vinod Khosla, who was one of the founders at Sun, said, "Gee, the reason we got going was everybody was out there ready to buy an 8600. But we took all the money that had been budgeted for the VAX replacement or the 780 replacement, and we filled them up with workstations." So there were a bunch of things that were that happened in there. This, by the way, this diagram here is one of of a kind of a. This has got the whole world on it, which you can only. I said I wanted to show this on the grounds that everybody would have a hard copy or can get a printout of it. But anyway, I think it really marks the different eras and does cover the. In this case, it goes from 45 to 2000. So it's a long piece of time. And I was doing some annotation of this today and putting different things on it, which I'm not going to do now. But it turns out that if you look at it, that it's there's a remarkable clock rate of what I put on as events, and that is it's a 12-year cycle, which is 2 6-year cycles, which is four 3-year semiconductor cycles. So there's, I believe in the I believe in the process evolution, 3-year process gestation of semiconductor process has been the clock and pretty much till now. It may still be, I don't know, but it certainly. As I marked events here, it was like clockwork of the major events corresponded to a 3-year clock or 6-year clock beat. Now we got a couple of choices. One is I've got things at the I've got another another section here that I could go over, or we could go into this is on sort of organization and culture. That was came out of a thought. I've used Ed Schein's book as kind of a framework here, or we can stop and just go into questions. Which would you prefer?
Ed?
Ed.
People have questions? Do you want to hear the culture part? We've got about another minute or two.
Maybe a real brief thing.
There's a vote for the culture on this end, Gordon.
Okay.
Hey,
Let me
Gordon,
go.
I have to catch a plane to New Jersey later tonight, so I actually do have to leave at 20 after or so.
Okay, well, take these slides with you. It'll keep
I
you
got 'em.
busy all night. And then, okay. These are Campus's slides, and I love this one, which you can't read. It starts with cultural sources and all up, and then external environment. Let me not do that. This is a thing that a little bit of a comparison with Microsoft. Let me go back here. Wait. I'm back. Okay, this is Cusimano and Selby. This is a very old description that Cusimano wrote, but I think in fact it's really I think characterizes. It seems to be still fairly typical of what Microsoft is like in terms of its values and how it operates. That is certainly this sort of predominant thing of finding smart people and really driven in that way. I wish I could say, from what I know, everything is done in small teams. I don't think I can say that. There's certainly a lot that the times when that's violated is when Microsoft gets in trouble, when there's just too many people working on something. This is absolutely true of pioneering and orchestrating mass market. Everything from the phone, the phone, places where one is leading versus where one is trailing. And I'd say the thing that I feel probably the most proud of Microsoft about, that's probably the least known, is all the stuff that's going on with TV, the IPTV, the media center. All of those were really pioneering systems. They've taken years and years to get profitable. They're still not mass markets per se, but in fact it characterizes the way that Microsoft works to continue to work on. It finds that it has a direction, it stays there and stays in it. So in fact it focuses on evolution and then working to those goals. So I think that those are really important attributes. This one here, this last one, attack the future, be in the mainstream. I think mainstream is real. There's a huge amount of attention to that. Bill and everybody else has got a very good antenna on that issue of the mainstream, whether it's the home, this service-oriented architecture, whether it's software as a service, games, the cell phones, whatever. So these are all things that I think are, for what Microsoft wants to be, are important attributes. If I look at Shine had said in terms of his attributes he thought were really important. That is, active problem solving, so that there's like Microsoft, there's always a lot of conflict coming up. That is, there's always a lot of how should you do something, and very often it leads to multiple, too many things, trying too many things and too many overlapping stuff. A lot of personal freedom, a lot of people who have to take responsibility. A thing that I had coined a word, saying that I had coined at DEC was never separate the planning from the execution. So that and then I do that by these four words then. So it's he who plans does. So you basically, if you're going to do something, you don't say, hey, I got this great plan, we're going to conquer this. Well, fine. Who's going to do it? Well, get those guys to do it. And if you don't do it, you're stupid. And that comes from not having staff and not relying on significant staff, and having separate, particularly the thing that often happens in an organization is a separation between marketing and engineering. And at DEC and actually at Microsoft, the product marketing and product management are with the development group. And this was the way it was done at DEC. There was every 4 years there's the marketing, there would be a big fight brewing, and somebody would say, they would come after me and say, I want all of your marketing product managers. We want to move all the product planning, all the product management into a separate organization that's independent of engineering. And every year that contributed to my heart attack, I think, a little bit of no, you're not getting those people, because when you separate them, why then who's responsible for the thing? It's, because it's like the marketing guys are, well, I told you what to build, you just couldn't build it. And so you have to negotiate that very contentious boundary, I'd say, as close to the product and the decision making as you can get. So lots of run with conflict. In a technical organization, there is inherent conflict all the time of how to do something or what approach to use, and then getting how you decide to get buy-in. There's a bit of let the market decide, and this was where I would say I didn't really agree with the 3 PCs of let's not let the market decide. I think there's, if you're going to do the 3, I mean, if you do them. I could have gotten rid of one, and it probably would have been the PDP-11 one. But certainly it wasn't set up for winning, and that was pretty clear right at the announcement.
What if you floppy disks were compatible too?
Right,
Fact,
file systems.
You picked a proprietary floppy disk format, which I couldn't even port IBM PC software to your machines.
Oh, that was on the PC.
Yeah, on the PC in the Rainbow. You couldn't read floppies.
Oh, that was a disaster.
Yeah.
Absolute disaster. When I was at NSF, Ken sent me, he said, here, I'm going to send you a DEC PC. And I got it, and it didn't have any software. And he said, well, I get the software from this company. That software doesn't work.
That's right.
And I said, this is insane. What is this? Don't you get it? And it was a beautiful piece of hardware, but it wasn't a PC. And this was in '86, and so this was after that whole thing had been settled. There wasn't anything to decide. The standard was set. You don't make anything else. And yeah, that was a pathetic thing. On the other hand, if you look at our keyboards today, it is the DEC. The keyboard I'm on is the LKO1, which had I think at the time I ridiculed it as head of engineering. It had 100 people working on, met and talking about the standard, and we had the DEC keyboard standard. But on the other hand, it turned out to be something that's lasted 30 years or so in terms of a standard.
Washington again. Regarding let the market decide, one of the takeaways I got from the Shine book was that DEC really didn't understand that market. They had focused for so long on the scientific and technical customer and embraced that customer base to such an extent that there was almost a disdain for the general computing or non-technical computing market, so that when there was an effort to court that market for financial reasons, they really didn't have the DNA to be able to grok that market.
Well, I think certainly the PC was certainly quite different from that, from what were the, I'd say, the market segments, because DEC was in several financial market or commercial market segments with VAX and all of that. So they did have customers that were in there, and we were doing quite well in that. I'd say a flaw that's probably is out of the whole, that's not so much in this presentation, is that DEC on that steep part of the up curve, DEC hired like mad. They hired IBM people, and basically when you brought these IBM people in to sell something, they basically, to the old line DEC customers, they were basically thrown out. They said, if we want to buy from IBM salesmen, we'll go to IBM. And fundamentally, IBM and DEC traded places in terms of how they marketed and what they did. So that whole segment, that I'd say half of the DEC failure had to do with products, product strategy, things that I've already talked about. But the other half had to do with the way they were doing the marketing and and addressing the market. Especially with having really knowledgeable people, going in versus having very high overhead people that in fact required having a lot of support and who didn't know the product. So it was a change. Everybody, particularly people in the sales organization, reflected on that. Sheridan.
Yeah, I'm going to make a comment. I worked at DEC from 1985 to 1995, and so I saw the height of DEC, and Ken Olsen was on the cover of Fortune magazine, and then I saw the demise. I saw what happened. There's one issue inside of DEC that happened over and over and over again, and it was lack of vision. Upper management did not see what was going on in the market as a whole. It wasn't marketing, it wasn't engineering. They were just trying to do the best that they could. It was upper management. It was Ken Olsen and then Bob Palmer failed at it, and the board, and quite frankly the executive committee. And that's why DEC fell apart, which is probably the story of every failure in any market.
Yeah, I think you can't. Thank you. I think that, I have that. I think that whole thing of, I guess this is really my final summary one of that deals with that. The top three exec didn't understand computing. They didn't feel computing. They didn't, it was like, Ken was on the Ford board. I think he helped them redesign some of their wiring around their engine. He was proud of that, and rightfully so. But the problem was he didn't have this. Even though he had built the first core memory computer, he really didn't have that feeling of what a computer is and what potential the computer had. And it was the vision of where are these things going. I mean, it's like anyone who's in computing really in computing say, what do you do? we had this aspiration. It's like having a child, this sort of growing child that grows exponentially, and you've got this aspiration for it, and you could see that there's no reason you can't do that, but you know you can't do it now. They can't jump 50 feet high because, well, we don't know how to make the springs or this or that, so we're limited all the time. But the issue of vision, the fact that Ken said, gee, who would want a PC in their home? I had written a memo in 1965 when I was, or 67, I guess. I was at Carnegie. My children were on a crappy IBM time-sharing system, using it, and I say, hey, we've really got to understand this. This is really an important thing. It's a little early, by 20 years, but on the other hand, it was an important thing. So he didn't have. I think it's vision and also aspiration. Didn't understand this issue of levels of integrations, make-buy, the importance of software and the independent software vendors. Because DEC had pioneered multiple channels. It went to the market, and in DEC's failing period, basically the guys in sales said, let's get rid of all of these channels because they present conflict. You can buy a computer from this guy or that way through these channels. There's all different markups. Let's get rid of all those. Well, it turns out all those channels, it got rid of them. They got it organized. But they also got rid of the software. They got rid of the vendors that were actually making the stuff work because they didn't understand how hard it is to get a computer to really work in an organization. And a lot of the ISVs and system integrators, that was their job. And people thought, oh, they're ripping us off by taking margin from that. That IBM picked that absolutely up in the mid 80s, totally copied the DEC strategy, and then really used it to wipe DEC out in that. So in fact, they were out of control from just in a numbers standpoint. Too many people per revenue. So because you've got to run your company and all of those things. These are all things that, in fact, I certainly had strong opinions about, and but again, I didn't think it was like giving up my life for them. But the other thing was that the technical ones, but the marketing organization and the top were really important.
Gordon, thank you. Fantastic. Thanks.
Okay.